Welcome, my name is Dr. DrWedding, and this is DrWedding DC22. Nodal Analysis with voltage and current sources. In this video, you will learn how to solve series parallel circuits that have more than one power source in them using nodal analysis. These sources may be voltage sources, current sources, or both. Nodal analysis is based on Kirchhoff's current law, and if you do not understand KCL, you will not understand nodal analysis. If you are unfamiliar with KCL, you may want to go back and watch DrWedding DC18. As a quick review, KCL states that the sum of the currents entering and exiting a node will sum to zero. A node is where three or more wires meet. The KCL equation is shown below. This circuit has already been solved, but the current values can be used to demonstrate Kirchhoff's current law. A node is where three or more wires meet. There are two nodes in this circuit, the upper node and the lower node. Starting with the upper node, if you add the currents entering this node and subtract the currents exiting this node, you will see that the currents will sum to zero. The same is true for the lower node. If you add the currents entering this node and subtract the currents exiting this node, you will see that the currents will sum to zero. This very simple concept is the basis for nodal analysis. Nodal analysis is based on KCL. You will sum the currents entering and exiting each node and set the equation equal to zero. However, the currents are unknown. To fix this problem, you will create a temporary voltage at each node. Using the temporary node voltages and resistors, you can rewrite the KCL currents in terms of the node voltages. This will reduce the number of variables so the equations can be solved. Once you solve the equations and get the node voltages, you can calculate the currents. This may sound confusing, but it is very easy, and it will become clear when you see an example. Nodal analysis will be demonstrated using the circuit below. As always, you start with creating a table. Then you can follow these 9 easy steps to solve this circuit. Don't panic. Each step is very easy, and solving the circuits will only take a few minutes. Step 1. Label the negative side of the voltage supply as 0 volts. Nodal analysis is used to find the voltages at each node. So, you start with marking the node voltage that is known to be 0 volts. Step 2. Draw arrows to represent the currents entering and exiting the nodes, and give these arrows names. You need to draw arrows at every node except the 0 volt node. In this example, you will only have to add current arrows to the upper node. If you are worried about what direction the arrows need to point, don't be. You can't pick the wrong direction for your arrows. Step 3. Write the KCL equation at each of the nodes using your chosen current directions. The KCL equation is shown below. I1 is positive because it is entering the node. I2 and I3 are negative because they are exiting the node. Because there is only one node with arrows, there will only be one KCL equation. You can't solve the KCL equation because you have 3 unknown currents. You need to reduce the number of variables. To reduce the number of current variables, you will add a temporary voltage at each node. Then you will rewrite the KCL equations in terms of a voltage divided by a resistance. Step 4. Add a temporary voltage at each node. We will call the temporary voltage at the upper node V1. There is no need to create a node voltage for the lower node because we already know the voltage is 0. Step 5. Write each current in terms of the voltages and resistors. From Ohm's law, the current through the resistor is the voltage on the high side of the resistor minus the voltage on the low side of the resistor divided by the resistance. It is very important that you get this equation correct. The voltage will enter on the high voltage side and exit on the low voltage side. In this example, the arrow representing the current direction starts at the 6 volt supply. This means the 6 volt supply is the high voltage. The arrow representing the current direction ends at the node voltage V1. This means V1 is the low voltage. Therefore, the voltage across the resistor is 6 volts minus the node voltage. Let's look at how the equation would change if you had chosen the opposite current direction. In this updated circuit, the arrow representing the current direction starts at the node voltage. This means the node voltage is the high voltage. The arrow representing the current direction ends at the 6-volt supply. This means the 6-volt supply is the low voltage. Therefore, the voltage across the resistor is the node voltage minus 6 volts. When the circuits and the equations are side by side, you can see that the equation will change depending on the direction of the arrow that represents current flow. Using the arrows chosen for this circuit, 3 current equations can be generated that are made up of voltages. The I1 current starts at the 6-volt supply and ends at the V1 node. This voltage is divided by the resistance between the 2 voltages. The I2 current starts at the V1 node and ends at 0 volts. This voltage is divided by the resistance between the 2 voltages. Finally, the I3 voltage starts at V1 and ends at 0 volts on the lower node. This voltage is divided by the resistance between the 2 nodes. Step 6. Substitute the newly generated current equations into the KCL equation. When the 3 current equations are plugged into the KCL equation, the KCL equation becomes a new equation with 1 variable in it. Step 7. Solve the equation to find the voltage at each node. This equation can be solved by simple algebra, but in more complex circuits, you might have multiple equations with multiple variables. In order to solve this equation or more complex equations, I use the online calculator found at the link shown here. This link is also in the description below. And while you're there, give me a quick like and a comment. By typing the equation into the calculator and pressing the Go button, the calculator lets you know that the voltage at V1 is equal to 4 volts. Step 8. Using the voltages and resistances, calculate the currents. From Step 7, you know the voltage at the node is 4 volts. So you can plug this value into the current equations from Step 5 and get the value of I1, I2, and I3. Because you found the node voltage V1, you were able to determine I1 is 10 milliamps, I2 is 5 milliamps, and I3 is also 5 milliamps. Step 9. Fill in the table. Start by adding the currents you just calculated. From your knowledge of series circuits, it is obvious that the current in R1 is also the total current. And using Ohm's law, you can easily fill in the rest of the table. With the filled-in table and the current directions marked, you have the complete solution for this circuit. Now that you have seen the procedure once, you can try a slightly more complex problem. This circuit is a bit different. It will have 2 KCL equations and 2 node voltages. But don't worry, it follows the exact same steps as before. Example 1. Solve this problem using nodal analysis. As always, start by generating a table. Step 1. Label the negative side of the voltage supply as 0 volts. The negative side of the voltage supply is 0 volts, but it stops at resistor R3. So in this circuit, there are 2 nodes with a non-zero voltage, and both of these nodes will need to have current arrows added to them. Step 2. Draw arrows to represent the currents entering and exiting the nodes, and give these arrows names. Step 3. Write the KCL equation at each of the nodes using your chosen current directions. Because currents that enter a node are positive and currents that exit a node are negative, the KCL equation for the upper node is I1 minus I2 minus I3 equals 0. And the KCL equation for the lower node is I2 plus I3 minus I4 equals 0. Step 4. Add a temporary voltage at each node. Step 5. Write each current in terms of the voltages and resistors. The current I1 is assumed to be flowing from the 10-volt supply to the node, So the voltage across the 200 ohm resistor is 10 minus V1. The current I2 is assumed to be flowing from the upper node to the lower node. So the voltage across the 700 ohm resistor is V1 minus V2. The current I3 is assumed to be flowing from the upper node to the lower node. So the voltage across the two resistors in series is V1 minus V2. Because the two resistors are in series, they are added together. Finally, the current I4 is assumed to be flowing from the lower node to the negative side of the power supply. So the voltage across the 100 ohm resistor is V2 minus 0. Step 6. Substitute the newly generated current equations into the KCL equations. First, substitute the values into the KCL equation for the upper node. This updated equation is now in terms of V1 and V2. This process is repeated for the lower node. The KCL equation from the lower node is shown below. This updated equation is now in terms of V1 and V2. Step 7. Solve the equations to find the voltage at each node. The two equations are solved simultaneously using the online calculator. The voltage at the upper node is 6.25 volts and the voltage at the lower node is 1.875 volts. Step 8. Using the voltages from Step 7 and the equations from Step 5, all of the currents can be found. The currents are shown in the bottom row. Step 9. Fill in the table. You can start with the currents that you just calculated. From your knowledge of series circuits, you can see that the current in R1, R3, and the total current are all 18.75 milliamps. The current in R2 is 6.25 milliamps. Resistor R4 and resistor R5 are in series, and both of these resistors have I3 flowing through them. So 12.5 milliamps is added to the table for both of these resistors. Finally, Ohm's law will fill in all the missing values. With the circuit and the filled-in table, you have the complete solution for this circuit. Here is a second example. In this example, there are two voltage supplies. It will be a bit more complicated than the previous examples. Example 2. Solve this problem using nodal analysis. As always, start by generating a table. Step 1. Label the negative side of the voltage supply as 0 volts. Step 2. Draw arrows to represent the currents entering and exiting the nodes, and give these arrows names. Step 3. Write the KCL equation at each of the nodes using your chosen current directions. Step 4. Add a temporary voltage at each node. The lower node does not need a temporary voltage because the entire lower node is 0 volts. Step 5. Write each current in terms of the voltages and resistors. The 5 current equations are shown below the circuit. These currents are in terms of the node voltages. Step 6. Substitute the newly generated current equations into the KCL equations. So, the 5 current equations are plugged into the 2 KCL equations. To generate 2 new KCL equations where the new equations are in terms of node voltages and resistors. Step 7. Solve the equations to find the voltage at each node. The 2 equations are solved simultaneously using the online calculator. After typing in the 2 equations separated by a comma, you press the Go button. And the calculator lets you know the voltage at node 1 is 16.02 volts. And the voltage at node 2 is 11.26 volts. Step 8. Using the voltages and resistances, calculate the currents. The 5 currents are shown in the bottom row. Please note that current I5 is negative. Step 9. Fill in the table. Before you start to fill in the table, we need to deal with I5 because it is negative. This means the arrow is pointing in the wrong direction. Flip the direction of the arrow and remove the negative sign from the current. Now continue as before. Fill in the rest of the currents. And find the missing values using Ohm's law. With the circuit and the filled-in table, you have the complete solution for this circuit. The final example is a circuit with a voltage source and a current source. Solve this problem using nodal analysis. As always, start by generating a table. Step 1. Label the negative side of the voltage supply as 0 volts. This leaves 2 nodes that will require current arrows. Step 2. Draw arrows to represent the currents entering and exiting the nodes, and give these arrows names. When the arrows are added, the current source changes the problem slightly. First, you definitely know the direction of the current exiting and entering the current source. The current direction is in the same direction as the arrow in the current supply. Second, you do not need a current name for the current through or for because it is already known. You also know the current that exits the lower node and enters the current source. These 2 currents are 15 milliamps. Step 3. Write the KCL equation at each of the nodes using your chosen current directions. This is done the same as before, but this time one of the currents in each of the KCL equations is known. So you enter the value instead of a made-up current name. Step 4. Add a temporary voltage at each node. So V1 and V2 were added to the circuit. Step 5. Write each current in terms of the voltages and resistors. The 3 current equations are shown below the circuit. As before, the equation is the starting voltage, which is the high voltage, minus the ending voltage, which is the low voltage, divided by the resistance between the 2 voltages. Step 6. Substitute the newly generated current equations into the KCL equation. So the newly generated current equations are plugged into the KCL equations to generate 2 new KCL equations that are in terms of voltages and resistances. In these equations, the voltages are in terms of volts and the resistances are in ohms. So the calculated currents are in terms of amps. So the 15 milliamps need to be converted into 0.015 amps. That way, all of the currents are in the same units. Step 7. Solve the equations to find the voltage at each node. This will be done using the online calculator. The calculator solves the 2 equations, and you now know the voltage at V1 is 7.75 volts, and the voltage at V2 is 1.8 volts. Step 8. Using the voltages and resistances, calculate the currents. Because you know the node voltages, you know the voltage drop across each resistor, and in turn, you know the current through the resistors. The calculated currents are shown in the bottom row. Step 9. Fill in the table. Start with the currents you just calculated. From your knowledge of series circuits, you can see that the total current exiting the 10-volt supply, the current through R1, and the current through R3 are all 18 milliamps. The current through R4 is the same as the current exiting the current supply. So the current through R4 is 15 milliamps. The current through R2 is the sum of the 18 milliamps exiting R1 and the 15 milliamps exiting R4. So the current through R2 is 33 milliamps. This matches the value generated by the online calculator. Using Ohm's law, most of the remaining values can be found. There are 2 missing values in the table. Both are associated with the current source. Using Kirchhoff's voltage law, you can find the voltage across the current source. Start at the star. Follow the highlighted path and add the voltages together. Set the equation equal to 0 and find the missing voltage. When you are done, you will find the voltage across the current source is 9.7 volts. Once you have the voltage across the current source and the current exiting the current source, you can use Ohm's law to find the resistance seen by the current source. Here is the complete solution for this circuit. I hope this video has helped you understand how to solve series parallel circuits with multiple nodes and multiple power sources using nodal analysis. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.